actually. Yes, today we will give some example about the inverse of the any matrix, invertible matrix, of course. We know this method and from the last lecture, and also let's give this theorem. This theorem, and also it is important how to check that our matrix invertible or not. But be careful here. Our matrix should be n by n, otherwise it is not possible to get the inverse, to mention the inverse of the A. It's okay. Our definition is valid, invertible matrix definition is valid only n by n matrices. It's okay. Be careful. And here, so this theorem claims that n by n matrix take, and this matrix invertible if and only if our matrix row equivalent to identity matrix, and means start with A is okay. If our aim is check that our matrix is invertible or not, use this theorem. Start with A. This one is a matrix. It's okay. For example, n by n matrix. So, and use the elementary row operation. Our aim is to get the reduced row echelon form. And then, for example, this one is reduced row echelon form. If this one is identity matrix, of course, this one is n by n. The order should be n. Identity matrix of order n. So this one is the reduced row echelon form. Reduced row echelon form of the matrix A, and means an A is row equivalent to identity matrix. It's okay, identity matrix. So if, and we know in this one, yes, A is invertible, means there exists the inverse. It's okay, but this one is if invertible, yes, our matrices are equivalent. If our matrices are equivalent to identity matrix, yes, this one is invertible matrix that exists inverse. It's okay. And now let's give some example how to check that and our matrix is invertible. If invertible, what is the inverse of this matrix? It's okay. Take this 3 by 3 matrix. It's okay. Square matrix, be careful. It's okay. Square matrix, 3 by 3. And first step, and write this matrix, construct this matrix. Take our matrix and add to the identity matrix or the same order. It's okay. So this one is A, this one is identity matrix. But our aim is to get the reduced row echelon form of this matrix. So our aim here, first of all, and use different color. I think it will be better. 1 0 0 here. We have leading one. Yes, our aim is to get 0 0 here, and one operation, first operation, multiply by -1, add to the second row, of course, to get 0. And the next one, take the first row, multiply by -5. It's okay. So, and the first one the same. Yes. Apply this one. Take this one, multiply by -1, add 1 1 0 1 minus 1. It's okay. -1 plus 1 0. -2 minus 4. It's okay. -3 plus 1 minus 2. -1 1 0. It's okay. This one. So the next one. Take this one, multiply by -5, and then add to the last row to get 0 in this position. So -5 plus 5, 0. -10, -2, minus this one, and -5 times this one, 15, -3, -18, -5, 0 0, 0 plus 1. It's okay. And our aim, and the next one, to get leading one of the next row, second row. It's okay. And look at the second row, and this one should be 1. So multiply by minus 1 over 4. And so we obtain this one. And also, but first of all, I think it will be better. First, use this step, this operation. Which one? Because look at the second row and the last column. And if take the second row, multiply by minus 3, add to the last row, we get 0 here. Minus 12 is okay here. And then 0 and apply the first this one, and then use this operation. It's okay. So we got this one and this one. It's okay. And the next one, to get leading one of the last row, and multiply by minus 1 over 2. It's okay. Our next row. So we obtain this one. Yes, this one is row echelon form. Sorry. But here, this theorem, this one should be, it is enough to say that our matrix is invertible row echelon, not you don't have to get the reduced row echelon form. It is enough, because what is the reason? Sorry, this one it is not. It is true, but not necessary to get the reduced row echelon form, and only row echelon form. But this one is not true. This one should be identity matrix, of course, reduced row echelon form. This one is reduced row echelon form. It's okay. This one is true. Sorry, this one is true, because and the row equivalent to identity matrix. But here, it's okay. But and wait, this part is okay. First of all, and apply the start with the this matrix. It's okay. This matrix. And apply the some elementary row operation to get row echelon form. Yes, we get row echelon form. Look at this one, row echelon form or not? Yes, but look at this one. It's okay. So, and we know that what is the method and to get the inverse matrix if our matrix is invertible. First step, construct this matrix. Second step, to get the reduced row echelon form, but this one is not reduced row echelon form, and then apply the sum operation to get reduced row echelon form, and this one is reduced row echelon form, for example. It's okay? But here, sorry. Let's come back our question. Yes. Here and this setup, it is enough to say that our matrix is invertible or not. What is the reason? Because our method, if look at the last matrix. If last matrix part, look at the part C. If part C contains 0 row means all of them 0, all entry. It's okay. So if this one first part contains 0, does not exist. Otherwise, yes, and C is non-zero row, and the C is, if this one is reduced row echelon form, this one is reduced row echelon form, C is identity matrix. So, and what's invertible? That exists the inverse. What's the inverse matrix? D, second part. And let's come back this step, this one, and our aim, if our aim is to check that our matrix is invertible or not. Look at this one, and this C contains zero row or not. It is not to get the zero row in the first part. Look at this one, because leading one, leading one, leading one. It's okay. So there is no zero row. It's not possible to get the zero row in the last step. So means, and look at this one, yes, we can say that our matrix A is invertible. And it means that there exists the inverse. It's okay, there exists the inverse. But in this step, use a different color. So the next question, if our matrix is invertible, what is the inverse? It is not possible to get the inverse here. It's okay, but this one is not the inverse. So you have to apply the sum operation here to get the inverse matrix. It's okay. Inverse matrix. So now, yes, our aim, and here, check that our matrix is invertible or not. If there exists, what is the inverse? It's okay, sorry. Inverse matrix. So, yes, and apply the more operation to get reduced row echelon form, and take the last leading one, we know, and this one. Our aim is to get zero, this part is okay, zero part. So, and start with the last leading one, it will be better. And our aim is to get and the 0, 0 here. So what's the first operation? Take the last row, multiply -1/2, and to get 0 in this position. And then take this one to get 0 here, multiply -3. And then add to the first row. It's okay. So apply this operation. So we got 0, 0, 1. It's okay. What's the next step? And the previous and the leading one. Our aim is to get 0 here. 0 here. How to get 0 here? Take the leading one. It's okay. This one, leading one. So multiply -2, add to the last, first row, and we obtain under this one. Yes. So look at the first part. And this one is, we know that, and this matrix, reduced row echelon form, yes, this matrix is equal CD matrix. It's okay, CD. So has no zero row in the first part, so there exists the inverse. What's the inverse? Inverse is this matrix, A inverse. It's okay. Any question? Okay, no question. So the next example, determine whether and this matrix is invertible or not. If invertible, find the inverse. It's okay. So our matrix A here, 4 by 4 matrix, 4 by 4 matrix. So this one should be 4 by 4 identity matrix. I support order 4. It's okay. And use some elementary operation, of course, to get the reduced row echelon form. Our aim here, first of all, we get 1, 0, 0, 0. It's okay. And this one multiply by -1, 1, 0, 0. And the next one, to get sorry, and 1, this one is first row, 1 0 0, the second column should be. It's okay. Look at this second column, this one, but multiply by -1, and so this one should be 1 -1 -2 -1 -1. It's okay, this one. So our aim is to get here 1 0 0 part. It's okay. So, and I think and first of all, this one should be not second row. It's okay, because there exists a 0 here, and interchange the row, it will be better, this one or this one, but choose one of them. Which one is appropriate, I think, and they choose this one, because what's the reason? Our aim is to get one here, one here. So how to get one here? Multiply 1 over 2. So, and we obtain 1 2 0, 1 over 2, 1 over. But, and how to get 1 here? Multiply 1 over 4. And so this one should be 1. So 5 over 4, 1, and the 3 over 4, 1 over 4. And also there is no 0 and entry here. It's okay here. I think it will be better choose this one. It is easy to compute. It's okay, because this one is integer, this one is integer, this one is integer, and also this one is 0. It's okay, but depends on you. Choose one of them. If choose for example, and this one, and the choose, and the other person choose this one, we get the same and the result. It's okay, but I think, and this one will be better. It's okay, and the interchange row, and then multiply 1 over 2, we got 0 1, and this one. It's okay, and interchange this one and this one. I think it will better change this one and this one, and also it's okay, but here not change, and yes, this one. It's okay. So the next one, to get 0 here, how to get 0? This one should be 0. So multiply -1 over 4, and then we obtain this one. It's okay, not this one. Yes, this one. So this one is not reduced row echelon form, and we obtain, and for example, and we get this one. Our aim is to next one to get 1, and our aim is to get this shape, and also it's okay, interchange row, and then multiply 1 over 6, and take the last row, multiply by this scalar, and then we obtain this one. It's okay, this one is row echelon form, this one, but not reduce. To get reduce, our aim is to get 0 0 0 here, and apply these operations, so we obtain reduced row echelon form. This one is identity matrix, so means our matrix is row equivalent to identity matrix, means our matrix is invertible. What's the inverse? Inverse second part. It's okay. So our matrix is invertible. Any question? Okay, no question. I think yes, no question. But here we claim that this one is our the inverse of our matrix. How to check that this one is true, and compare to this product. If this product is identity matrix, yes, it's true. It's okay. And also, of course, should be, and this product is this one, and also it's okay. This one is our result. It's okay. This one. take our matrix here. This one is our matrix. This one is, we claim that this one is the inverse of our matrix. So, and they use compute this product, and then we obtain the identity matrix. Yes, this one is identity matrix. So yes, our matrix is invertible, and also the inverse is right. It's okay, true. Okay. Now one more example here. It's okay. Find the inverse of this matrix. This one. So let's skip under this one. Yes. Look at this matrix. Find the inverse of the matrix A if there exists. Is okay. So and use the same method. Construct this matrix A, identity matrix 3 of order 3, and we get 1 0 0, of course, and so we obtain 1 1 0 here, and multiply minus 3, add to the last row to get 0 here, and how to get 1 here, minus 1 over 4 multiply by, and then, but here, look at this part, be careful, our aim is to get 0, multiply this 1, so we get 0 here in the arbitrary step. So this one is, and it means, and this one is not C, not reduced row echelon form, but this part is row equivalent to C. If and this matrix contains 0 row, and means, and more step, apply more step, we get C, but and the C has 0 row, and C has 0 row here. It's okay. Is C is row equivalent to this matrix, and but has 0 row, so A is not invertible matrix, does not exist the inverse. It's okay, means. Any question? Okay. Now sorry. Now let's define the determinant. Determinant of any matrix, but of course our matrix should be a square matrix. It's okay? Square matrix. Be careful. Let's define determinant. Now, and they take here n by n matrix. It's okay. R matrix A, for example, take R matrix n by n, dimension n by n. First of all, be careful, should be square matrix. It's okay. Otherwise, it is not possible to mention the determinant of A. What's the determinant of A? Determinant of A, take the R matrix and find the number, real number. It's okay, this one. And because our space and real numbers, it's okay. Sometimes and consider complex numbers, it's okay. But here in our lecture, consider real numbers. It's okay. So and they take our matrix. So because and here in our lecture, our matrices over the coefficients coming from and the real numbers. It's okay. But of course, consider this one the same and the property. It's okay. But here, consider only these matrices. Entries coming from and the real numbers. Okay. Sorry. take the our matrix. So, and this matrix gives the one number is okay here, and the real numbers is okay. For example, and alpha is a real number. It's okay. For example, and this one is called. It's okay. It's the determinant of A. So what is this one? This number and the fixed number. It's okay. Depends on our matrix A, of course. This matrix gives this one. So how to compute? And our aim, this one is called the determinant of A. This one is determinant of A. Determinant of A is noted by this notation. A is a matrix, capital A, and use this notation. It's okay. Determinant of A. This one is determinant of matrix A. It's okay, this one. And here, how to find this one? First of all, the problem, take our matrix, find the determinant of A. And first of all, transform, and we can transform this problem and to the new problem. What's the new problem? And take our matrix A. It's okay. We got here n minus 1 by n minus 1 matrix. But this matrix does not the A matrix, because the dimension n by n, this one dimension n minus 1, n minus 1. So, and the first problem, and take our matrix, and we get the n minus 1, and the matrix is okay. So our problem is evaluate the determinant of the n minus 1, n minus 1 determinant. It's okay. So what is these determinants? This one. It's okay. These determinant. So, and repeat this and use some method to apply, and this one we obtain the n minus 1, n minus 1 matrix. It's okay. Here reduce our problem to the evaluating the determinant matrices of n minus 1, n minus 1. So, and repeat this process, and then we get 2 by 2 matrix. 2 by 2 matrix. So our aim is to get 2 by 2 matrix, and we know that 2 by 2 matrix and it contains 2 rows and 2 columns, A, B, C, D. It's okay. So our aim is to compute the determinant of the 2 by 2 matrix. It's okay. So, and if we know this one, yes, it is easy to compute the 3 by 3 determinant, and then this one, and we obtain alpha. It's okay to process this one. So, and what is this determinant? This determinant, 2 by 2 determinant, is this one. You know, maybe this one, and take A and C, not AD, and AD, and minus BC. It's okay, this one. But and how to get this one is okay, and also we obtain the determinant of A, n minus 1, n minus 1 matrix here. Yes, and we claim that, and take for example, let our matrix A is denoted by this notation: I, J entry, B, n, n by n matrix. N by n matrix is okay. N by n matrix, use the black one. Yes, n by n matrix. And so our aim is to get the submatrix of matrix A. How to get submatrix? Submatrix means delete the sum and the row and column, we obtain the matrix. This matrix is called the submatrix of A. It's okay. So and let's define the new matrix Mij. But this matrix n minus 1, this one is our matrix A, n by n, mij, new matrix, and n minus 1 by n minus 1 matrix. It's okay, matrix. So how to get this matrix? This matrix is a submatrix of matrix A. Look at our process, and it's okay, and start with n minus 1, n by n matrix. So we obtain this one, reduce the problem, and to find the matrix n minus 1, n minus 1, and this one. This one is a submatrix of A. It's okay. So, and is noted by mij. So how to get this submatrix? This one is obtained by, and take the R matrix with the sum and the row and column. It's okay. The ith row and jth column on matrix A. What does it mean under this one? It's okay, this one. For example, our matrix A, this one, and the row is okay, this one, and sorry, this one should be it's okay. Choose and the row I and choose row J, column J. This one is column J. It's okay. So and delete and this column and this row. This one is n by n. So we obtain new matrix. So and the dimension of new matrix n minus 1 by n minus 1. Yes, this one is noted by capital M sub ij. It's okay, ij. Ijn means, and for example, this one is m2, 3, and means take the R matrix A and delete and the second row and the third column, and so we obtain m2j, 2, 3. It's okay. So and this and this and the matrix is called the minor. It's okay, minor. This one is called minor of entry ij. It's okay because and take the look at this one. ij here is okay. So and the minor of ij and means find and this entry and find the position. So delete this and the row and column. It's okay. So it's called the minor of and this entry aij. It's okay. This one is the minor. So and let's define the and the cofactor. Is noted by capital Ij of entry Ij. It's okay, Aij. And this one is defined as, and this one is, and take the minor, Mij, and this one is a matrix. Compute the determinant, Mij, multiply by minus 1 to the I plus j. This one is called and cofactor of and our entry. It's okay, this one. So and of course now the question, R matrix A n by n, but and here Mij n minus 1 by n minus 1. It's okay, this one. Determinant of the and this matrix. It's okay. So what is the and the determinant? Determinant of A is denoted by this notation or this one. It's okay. And we can use the first and the notation. It's okay. What's the determinant of A? And take the any row or column. It's okay. And write the all entry of the corresponding and this and the row. It's okay. And write all Aij, and for example choose the row I and write the all entry of row I. So j is 1 to n, multiply by the corresponding cofactor. It's okay, ij. So what does it mean, this one? And write the all entry of row I, and the first one I sub 1, the second entry of row I sub 2, and the last entry I sub n. Write the corresponding capital A, I1 plus I2 plus In. And this one is called the determinant of A. This expression is okay. Expansion of determinant of A is okay. Determinant A along the ith row, this one, because choose the arbitrary row, and here row I is okay. And for example this one, and this one, the entry of row I is okay. But we claim that, and here take our matrix A and choose the row I sub 1, I sub 2, and the last entry I sub n. Choose this one, row I, is okay. So, and find the determinant of A depends on row I. Write the all entry here, it's okay, and then multiply by the corresponding cofactor. It's okay. So, but this one gives the determinant of A. And for example, first of all, we can choose the first row, and we obtain determinant of A. And for example, and one of them, choose the last row, we obtain determinant of A. But here we claim that this one and this one the same, not depends on and the row. It's okay, which row, and so we obtain the same value. It's okay. This one is a fix. Let's come back. Take our matrix, this one, and we get the determinant of A. This one is a fixed number. It's okay. For example, we obtain 2. It is not possible to get the 2 and 3, for example, or 5. But one of them, it is true. It's okay. It's not possible to get the 2 real numbers. Okay. So fixed number. So and also we claim that determinant of A, and they take the any column, for example column J. So first entry A sub J1, the second entry of the second this column J2, and the last one A Jn. Take the column J, and this one gives give the formula for determinant, and this one is summation I J I is 1 to n, and this one 1j Oh, notation here it is not true. Not J1 because row not J. The first row J column 1J. Sorry. This one is 2J. 2J. This one is the last entry of the J column. And this one in the last row and J column. Sorry. So, and the first entry of the J column, 1J. The second entry of the column J, 2J. The last entry, NJ. And multiply by the capital A, 1J, 2J plus NJ. Okay. So, and this one is called expansion of determinant of A along the J column. So, and here we claim that take the any row, for example, choose the row I or choose the column J, and so we obtain determinant of A, and this one gives the same number. It's okay. So let's give an example to understand this definition. It's okay. This one. Let's come back here. Yes, let's give example. Yes, and the 2 by 2 matrix. And what is the determinant of 2 by 2 matrix? And here, and the minor, and this one is okay. And so we obtained this one. So, and here, A, B, C, D, determinant of A, B, C, D, A times D minus B, C. It's okay. This one is positive line, and this one and the main diagonal entry, and product of the all entry on the main diagonal AD, and this one is line minus, and the entry product of the entry on this line minus BC. It's okay. So, and so the next one, 3 by 3 matrix, and compute the determinant of 3 by 3 matrix. So how to get, and you have to find the minor and compute the determinant. What's the determinant? Depends on you. It's okay. Choose the one and the row or column. First of all, for example, choose the first row. It's okay. Our aim here, find the determinant by using and the row expansion, first row expansion. It's okay. So means determinant of A, write the all entry, A sub 1, 1, A sub 1, 2, A sub 1, 3, and multiply by the corresponding cofactor, and A sub 1, 1 plus 1, 2 plus 1, 3, 1, 3. It's okay, this one. So we know the entry. Look at the first row and write. So our aim is to get the ij and this one. But we know that this one is equal minus 1 I plus j minor, determinant of the minor. So let's find the determinant of the minor. So how to find, for example, find this one, m sub 1, 1. M sub 1, 1 is a submatrix, and how to find M sub 1, 1, and means delete the first row and first column, and then we obtain submatrix. Submatrix this one. This matrix is called minor. And compute the determinant. So right here determinant, but parentheses, it's important. This one is not matrix. This one is determinant of the minor. Minor is a matrix, but our aim is to compute the determinant of the minor. So we know 2 by 2 matrix and the determinant, how to compute, and the sun and minus. It's okay? So, and compute the next minor M12 determinant of A. So means how to find submatrix such that 1, 2 and means first row and second column. So our matrix A2, 2, 1, 2, 3, 2, 3, 3, 1, 3, 1, 3, 3. A, 3, 3. It's okay? So, and the next minor, and M13, 13 means first row and column 3, and we obtain this one is M13. Compute the determinant of A 2 by 2. We know how to compute. Yes, multiply and this one and minus this product. Yes. Any question? No question, okay. So determinant of A and multiply by the as a 1, 1. So take this 1, multiply by as a 1, 1. It's okay. So we obtain this one. And but what is the a sub 1, 1 minus 1 to the 1 plus 1 and 1, 1. So this one is even number 2, and so m1, 1 determinant of m1, 1. It's okay, this one. So what's the a sub 1, 2 minus 1, 1 plus 2 minor 1, 2 determinant of a, but this one gives minus minor. So, and this one multiply by minus 1 and multiply by this one 1, 2, 1, 2, this one 1, 2, this one, but multiply by minus 1, minus and plus. It's okay. And then the next one, compute to this one, 1, 3 multiply the corresponding capital A1, 3 and this one. It's okay. So multiply this one. So we obtain this term and this one, the last term. So our determinant we obtain this one. But and the sum and the positive and the term and this one is the positive. This one is the positive, and also this one is the positive. Positive, and this one is negative. So we obtain the determinant of A. And also we know Sarus rule, and the Sarus rule gives the same result. It's okay. But and in our lecture and don't use the Sarus rule. If use and the exam and for example compute the 3 by 3 determinant our question. If you use the Sarus rule and to get and not full credit and the 0 grade, it's okay, great. Because don't use the Sarus rule or in our exam. It's okay. But here we give the Sarus rule. What's the Sarus rule? But Sarus rule, be careful. And the Sarus rule only valid for and the 3 by 3 matrices. It's okay. Otherwise, it is not true. It's okay, not valid. Be careful. What's the Sarus rule? Write the R matrix, and this one is R matrix. It's okay. This one is a 1, 1, 1, 3, 1, 2, 1, 3, and the second row and the last row. And take the first row and the second row. Repeat first row and second row. So we obtained this one. It's okay. Obtain this one. So and sketch the sum line and the first line and this one. This one is positive. This line is a positive line. This line is a positive line. It's okay. So and take the all entry and multiply by all of them and write this product. And first look at the first positive line, and the first entry this one, second one this one, and this one. So write the product of the all entry on the diagonal. 1 1 2 2 3 3 is a positive. Another positive line, the second one, this one is okay, and use a different color, maybe it will be better. It's okay, this one. Another positive one, this one, and the first entry this one, the second one, and this one, and the product of the all entry on the line, and 2 1 3 2 1 3. This one is positive, and also the last positive line and this one, yes, this one is plus 3 1 2 1 2 3. And look at this one. This one is this one. This one gives this one. This one is equal this one. It's okay. And also now, and sketch the line, other line. It's okay, a negative line. This one gives the minus line, another minus line, and this one. Sorry. And the last line, this one is minus sign, minus sign. It's okay, this one. So take this one and the product of the all entry, minus 3 1 2 2 1 3, and another minus this one, minus this one, and this one. It's okay. It's up 1 1 3 2 2 3, and minus the last one, this one. So look at this one and this one, this one, this one, this one, and this one, this one, and 3 1 minus 1 3, this one. It's okay, and this one is this one, and also this one should be this one. So we obtain the same result. It's okay. Sum of the product all entry on a positive line and minus negative 1. It's okay. So guess then the determinant. Let's give the more example. For example, look at this one. 1 3 4 2. It's okay. So multiply by this one. 1 times 3, we obtain 3. 2 times 4 and the minus 8, and so we obtain the result minus 5. So look at this one and this use the, and our aim is to get this one. It's okay, and use the Sarus rule, and we obtain this one. And let's give an example, but don't use the Sarus rule. It's okay. But first of all, let's have a break, and then we will give the example how to use this method. It's okay, 3 by 3. Don't use the Sarus rule. It's okay. And the 10 minutes, it's enough, I think. It's okay.